Hey guys, today we're going to have a look at one way to detect anomalies in time series data, and we are going to do that using deep neural nets and more specifically LSTM Autoencoders. So we're going to do that using Keras and TensorFlow tool, and we are going to detect anomalies in S&P 500 daily closing price. So let's have a look at some of the data that we have for this tutorial, and the data comes from Kaggle, and it's provided by Patrick David. I've linked his Twitter account in here, so thanks Patrick for providing this dataset. And the dataset contains daily closing prices for the S&P 500 index from 1986 to 2018. So if you don't know what the S&P 500 index is, you can read this or go to the Wikipedia link. And I'm going to link all the tutorial and the source code of this for this video down in the description, so you can follow along if you like. So I've just opened up a new notebook in Google Collaboratory, and I've already used the GPU hardware accelerator for this, and as you can see I have the Tesla P100 in here, so this is great. And then I'm going to install TensorFlow GPU, so that this should install TensorFlow 2 for us using the GPU version of it. And then I'm going to do a bunch of imports. I'm going to set some seeds, and then I'm going to download the CSV containing the data. So this is where we actually start using and writing code and using the dataset. So the first thing that I'm going to do in here is to read the CSV file into a pandas data frame. Then we're going to have a little bit of look on the data, and then we're going to develop our LSTM autoencoder model. And I'm going to speak briefly a bit more about what LSTMs are, and more specifically what LSTM autoencoders are. So let me start with reading the data in here. I'm going to use the read CSV function, and as you can see we're downloading the file called SPX CSV. I'm going to parse the dates in the column called date, and I'm going to set this column as an index as well. So if I look at the data frame, we see that we have the date and the closing price for this particular date. Okay, so let me check the shape of this thing. Yeah, we have around 8k of examples in here, which is quite frankly not a lot, but yeah, we should do with that. So the next thing that I'm going to do is to plot the prices, so we can have a look at those. And I'm going to just do that. And yeah, this is a graph of all the closing prices, and as you can see after 2016 the prices are steadily increasing up until 2018. So this is the data that we have right now. So we are going to take just a part of this data, or 95% of this data, and use it to train our model, and then we're going to predict on the next year or so using our model. So the first thing that I'm going to do is to split the data, and I'm going to define a variable called train size, which is 95% of the data. Okay, so after we have that, I'm going to specify the test size, and this is just going to be the number of rows in the data frame minus the data in the training. So the next thing that I'm going to do is to take a subset of the data from the training set and a subset from the data for the test set using pandas iWalk method. Okay, so we're going to start from the train size and go to all of the length of the data frame. So this should divide our data set nicely, and I'm going to see the shape of both training and test data sets. So as you can see, we have just below 8K examples for training and 400 examples for testing. So these are for 10 days on which we are going to detect anomalies as a test data. Okay, so the next thing that we are going to do is to actually scale the data, and scaling is really important for most like machine learning algorithms, and in particular algorithms that are using gradient descent or similar algorithm to find the best parameters for your model. So we're going to use the standard scaler from the sklearn library, and I'm going to import that in here. Okay, so we're going to define an instance of that scaler, and I'm going to do the import just for the autocomplete to work, and then we are going to fit the train close price in here. So I have a typo. Okay, so we are fitting just on the training data, and this should be always the case for you because you want to use only the training data for all your models, and then you're going to test only, of course, on the test data. So you don't want a leakage of information, for example, like the mean of the whole data set that you have. You want to get the mean only on the train set, so you simulate the real world example as much as you can. So the next thing that I'm going to do is to apply the transformation from the scaler to the training close price and the test close price, again using only the parameters on the training data set. So to do that, I'm going to use the transform method on the scaler. And I'm going to do that on the test set, of course. So yeah, you might receive some warnings, but this should be alright, at least for now. So we've now scaled the training and test data and the closing price in those, so we can have a look at some of it. And as you can see, we have a minus in here, but that's just fine. The scaler did its job. Okay, so the next thing that we are going to do is to create the dataset that we are going to use for the LSTM model. Recall that the LSTM model is actually a type of recurrent neural net, so it expects some sort of a sequence, and we're going to create a dataset that we're going to create a number of sequences that create a number of sequences that use 30 days as a sequence for the closing price that you have. So for example, if we train our model, a single example will be like from the 1st to 30th of January in 1886 or whatever year, and the next example is going to be from 2nd January to 31st January of the same year, and so on and so on. And we're going to do that using a helper function called createDataset. And this function is actually really generic, so it works pretty good. Okay, so let's create this function. It's going to be named createDataset, of course. is going to take the x and y and a number of time steps that we are going to use. You'll see why in a second. I'm going to create two arrays or lists in here, and then I'm going to iterate over the length of the axis minus the time steps. So okay, so in here I'm going to take the current value from the x, and I'm going to do a bit of indexing. So this is just taking the value at the current time step that we're interested. So this might be like January 2nd, 1986 or something like that. We are going to append that value to the axis, and I'm sorry, this is going to contain not just that, but this is going to contain not the January 1st. This is going to contain, for example, January 1st to January 30th, depending on the number of time steps that we've passed in. So this might, in our example, I'm going to use 30 days as a history data, or we're going to use 30 days for creating the sequences. So we're going to take January 1st to January 30th in here, and we're going to append this value to the axis. And again, I'm going to do roughly the same thing for the y's, but I'm going to take the January 31st and try to predict its value, and this is going to be our label. We're going to predict its value based on the previous 30 days. Okay, so let me append that. And finally, I'm going to return those two arrays as NumPy arrays. Okay, so this function should be working now. And we are going to convert our train datasets into sequences that LSTM autoencoders will understand. And I'm going to define the time steps or the days that we're going to use as a history. And we are using only a single feature in here, but actually this is much more generic and you can use multiple features if you had those, but currently we have only the closing price, and I'm going to pass in the time steps. Let me check if this function actually works. Yeah, it appears to be working. And then we're going to do the same thing for the test dataset. Okay, so let me run this, and we're going to check in the shape of the X train, and as you can see, we have the same amount minus 30 of the sequences or the training data that we had already, and we have the time steps equal to 30. So this is the one in here, and the last dimension we have just the price. So this is the shape that we're going to use as an input to our net. Okay, so the final piece of the puzzle is going to be the LSTM autoencoder, and you should already know how LSTMs work. They just need a recurrence. They're just recurrent neural nets, and they need some sort of a sequence as an input. And the next thing that we're going to do in here that is a bit more interesting, I guess, is the autoencoder. And the autoencoder is not a layer in Keras or whatever. It's a type of architecture or a type of neural network that tries to reconstruct itself, the data that it has. So the idea behind all of this that we're doing is to basically train a model based on this data, and after we train this model, we're going to measure its error, and if it's predictive error, and if that error is above some threshold or below some threshold, depending on what you want to predict or do, But let's say if the error is above the threshold that you've specified, then your model can't reconstruct this data, and this might be an anomaly or a rare event. So yet again, I'm going to summarize it. If the error is larger than some threshold, then we will say that the current data point is an anomaly. And we're going to use that in the test set, and we are going to see if this works in practice, at least for this data set. So the model itself is rather easy to code in. So I'm going to start with creating a sequential model using Keras. I'm going to add in an LSTM layer, and it's going to contain 64 units, and I'm going to specify the input shape, and this is the shape that we've used in the sequences that I've showed you. Okay. So we have something like this. The units and then the input shape for this layer. Then I'm going to add in a dropout layer just for a regularization. And we're going to specify a rate of about 20%. Then here comes the interesting part. We are going to do a repeat vector, which is going to just copy the values that we have already. So this should return a sequence as well. And I'm going to specify the number of items is going to be the number of items in the first dimension, or this will be 30 in here. Okay, so again we have a sequence of 30 elements, and I'm going to do another LSTM layer. So I'm going to reconstruct the sequence that we had so far, and in here I'm going to specify another parameter that you might have heard of or seen, and it has the name of return sequences, and it's pretty much self-explanatory what it does. It's just returning the sequence after doing the parameter optimization in here. Then again, I'm going to add another dropout layer with the same dropout rate. And finally, I'm going to output a time distributed fully connected layer. So this layer is going to provide us with the same amount of units that we've passed in as the input. So basically what we're doing in here is inputting a sequence of 30 closing prices, and we're asking our model to predict the same sequence. But that's a bit different from memorizing the sequence itself. We are just severely regularizing our model and forcing it to learn the most important features of our data. And by that, we're going to then use the error that we had and threshold it and try to predict whether or not we have an anomaly on our hands. So let me add the time distributed layer. And the number of units is going to be, again, the number of features that we have, and that is going to be just one. In our case, we have just the closing price. Finally, I'm going to compile the model using the mean squared error, mean absolute error in here, and I'm going to use the Adam optimizer. Okay, so this should hopefully work. Okay, and then we're going to train our model. The training is pretty much what you'd expect. Well, I'm going to train the model for 10 epochs. I'm going to specify a batch size of 32, and I'm going to validate on 10% of the data. And here the most important thing that we need to do when training time series data is to not shuffle the data, because the data is history dependent. Or we don't have the assumption that the data is randomly is independent. Okay, let's start the training. Okay, so we're training on about 7K examples, and the training should be pretty fast, actually. So after the training is complete, I'm going to show you. Okay, I'm looking at the validation loss, and it's decreasing. Okay, so we have something like that. And as you can see, the validation loss has decreased steadily in here. And just for 10 epochs, we're going to have a look at the training. And yeah, as you can see, the training itself was a bit rough, but yeah, after 10 epochs, it seems like the validation error loss is a bit decreased, so it might be the case that our model has learned something. Of course, we don't have a lot of data. In the real world, you probably have a lot more data and train your model for a bit longer. But in here, we are going to just continue with this model, and we are going to take the predictions for the training data that we have in here. And you're going to see why in a bit. And we're going to calculate the mean absolute error on the training set. And I'm going to use NumPy to calculate that error. And I'm going to have a look at the loss. So these are just okay, so we have the error for each example in the training set that we had. So I'm going to show you something really cool. Okay, so we're just plotting the errors for each example. And as you can see, let me just unzoom this and do this. And as you can see, we have a lot of examples that have an error just below 1.5, for example, or something like that. So in here, we might take this value here, or maybe something a bit more extreme, a value of like 1.8 or something like that, and declare anything that has error more than 1.8 to be an anomaly. Okay, so let's continue with this, and we're going to do the exact same thing on the test data. Let me just rearrange. I'm going to take the predictions on the test set, and again I'm going to calculate the test mean absolute error. And then I'm going to show you how you can use that for thresholding. I'm just specifying the test mean absolute error. The threshold that we've picked is going to be 1.9. And let me just plot this by using this. Okay guys, so I had a typo in the create dataset. So the new fixed version will be linked down in the source code that I've linked down in the description. So the next thing that we're going to do is to have a look at the new plot. And as you can see, you might want to pick a threshold of about 0.65. And when you do that, we're going to use the test dataset. So we're picking the threshold based on the training dataset, and I'm roughly saying that it should be this value right here. So anything above that is going to be considered an anomaly. So let me just plot the values in here that are above this threshold. And as you can see, we are picking just a few examples in here that are just above this value. And in here, I'm just plotting the closing price against the threshold. The threshold was. So the last thing that we're going to do is to actually show. I'm going to actually show you the points at which we are saying that there will be an anomaly. And to do that, I'm going to use a combination of pyplot and seaborn. So we have the first thing that I'm going to do actually is to create the anomalies dataset, and this is going to be just the values that have anomaly equal to true in here. So the anomalies should be a small data set, and in here we have just 2 anomalies. So let me show you those. Okay, so these are the anomalies that our model is detecting, and you can go back and pick a rather more conservative value, so 0.6 for example, and then these are all the values that our model considers to be anomalies, and we have 4 examples now. So these are the anomalies that are considered by our model. So as you can see, the price is going up, and then suddenly the price is dropping, and then again we have a sudden change in here, which suggests that the model is expecting that the price to continue to go down, but in here it goes up. If we reduce the threshold even further, we're going to observe something more interesting, and in here you see that the anomalies are detected as well as in here and in here. So the less of a threshold, the lower the value, the more anomalies you're going to detect, of course. And depending on your problem, whether or not you are looking for anomalies in, let's say, server load time or anomaly detection in credit card data, depending on that, you might want to use a different threshold for selecting the anomalies. Of course, selecting this threshold might be an interesting problem from computational standpoint. You might try different values, and maybe you can read about, you can read about other ways or automatic ways to select this threshold, but this is just the basic way that you can use to detect anomalies in time series data. I hope you've enjoyed this video. Give it a thumbs up, subscribe to this channel, comment down below if you want some further clarification on the data that I've showed you here, and have a good New Year's Eve. Bye guys.